My name is Jean-Francois, and I'm a research fellow at the Active Inference Institute, where I carry out a research project in artificial agency. The title of my talk is the phenomeno-logical robot. So my research project asks the question, what does it take at a minimum for an autonomous robot to learn to survive in a world it knows initially nothing about? So in the hope of finding answers, I'm programming a mortal robot to have felt experiences, to make sense of them, and to grow the agency it needs to survive. The robot in question is a rover made of Lego EV3 parts that is equipped with a variety of sensors and motors. So what this project is not, first of all. Well, this is not an input-output simulation of human-level cognition, which is what LLMs do. It is also not meant to be a general model of cognition. It is, at best, an attempt at implementing one form of basal cognition for a simple robot. This is not a robot solving free energy principle equations in the same way that bacteria do not do math. And this is not a robot as an extension of its programmer. Very importantly, the robot's experiences are not going to be grounded by its observer. It has to make its own sense of its own reality. So what is this? What is this project? Well, I want to achieve basal cognition, not simulate the more complex human cognition. I am building an artificial agent, not proposing a general model of cognition, though this project is principled. Free energy principle is applied here as an analytical framework, not in implementation. It will be used, but a posteriori. And finally, experiences are to be intrinsically meaningful to the robot, and not necessarily to me, its programmer. So this project is a learning by building exploration, which is at the intersection of phenomenology, active inference, and agency. Phenomenology seeks to determine the essential properties and structures of experience itself, and to provide an objective account of subjective experience. So what is experience? And not, is this experience correct in terms of some objective reality? Active inference. Well, according to active inference, an enduring self actively infers the causes of its sensory input and shapes its niche to minimize prediction errors. And agency. Well, agency is the ability of a self to act purposefully, to achieve its own goals in an uncertain world it experiences. So my project is to program a robot so it learns to survive by experiencing, engaging, and making sense of its world. And the robot is to do so all on its own, unassisted by its programmer or some observer. Okay, so first let's look at the principles guiding this project. Well, to have agency, a self must be mortal. We take that position. I take that position. Agency implies a self that is distinct from its environment. I think that's pretty straightforward, though the self is not disconnected from its environment. So distinct but connected. The self is not a thing, but processes that are organized to endure. In other words, a self is a dynamic organization of processes that constrain and sustain one another. The organization is not fixed, but can adapt to avoid dissipation. What matters is the lack of discontinuity. A self's overarching goal is to survive, and survive in a dissipative environment it depends on. The processes that produce the self must adapt their organization to preserve continuity of being. A self strives to remain a self, but not necessarily to stay the same. Mortality is critical because it introduces value. What helps the self persist is good for it. What threatens to terminate it is bad for it. Value is subjective. Here we see a small bacterium that's breaching a larger one to feed on its insides. Well, clearly, what's good for one is bad for the other. So for our purposes, let's define an agent as a mortal self choosing how it survives. So to survive, an agent must make enough sense of itself in its environment to predict well enough the consequences of its actions or inaction. To endure, a self must have felt experiences. That's very important. So, what are experiences and where do they come from, first of all? Well, the agent's environment impinges on its senses, and so do the agent's own actions. The agent must constantly process streams of multimodal sensations. The agent integrates these sensory streams in space-time in order to create its experiences, actively create its experiences. So, for example, when I bite into an apple, I experience its taste, crunchiness, color, weight at once in unified moments of experiences. It's worth noting that an agent need not be aware it is having experiences in order to have them. But that's it's a different topic. I think if we go deeper into this, we start entering the domain of consciousness. Let's not do that. Not yet. So the agent keeps track of risks to its survival by constantly measuring its well-being. It is mortal, and measures of well-being indicate how its survival is at risk. Let's posit that the well-being of an agent is a function of three things. Its fullness, how energetic it is, its integrity, how healthy it is, and its engagement, how involved it is. And let's assume that the functions calculating well-being are predefined and unchanging. They are given to the agent at birth, so to speak. So the agent will correlate its experiences with fluctuations in its well-being, detected fluctuations in its well-being. And this is how it will have felt experiences. An agent can thus have good and bad experiences. So, sense-making. An agent must make sense of its world if it is to survive in it. It cannot just act blindly. An agent makes sense of its experiences by modeling what causes its sensation. It builds a causal theory. The causal theory explains what causes the sensations. The causal theory is used to make predictions. It is a generative model. It predicts incoming sensations. Now, actual sensations that contradict the predicted sensations become prediction errors. This happens when the causal theory is inaccurate or incomplete, or when the world has changed since the causal theory was formulated. So this is basic predictive coding, predictive processing principles. So what an agent senses will be the uncontested predictions it makes, plus the prediction errors it receives. So the perceived sensations are a combination of predictions and prediction errors. what the agent experiences then is limited to what it can predict. But what it can predict changes over time. Let's not forget that the causal theory that generates these predictions is going to be changing and evolving over time. So we remember that an experience is the integration of streams of sensation. And so an experience will be surprising when it incorporates sensations that are prediction errors. So the more prediction errors are integrated into an experience, the more surprising the experience will be. So at first, an agent will hold a trivial theory of causal theory, one that simply predicts that nothing changes. So it predicts unchanging sensations. But clearly, expecting a world that never changes leads quickly to many prediction errors. The agent updates its causal theory when too many experiences are surprising. As we've discussed, the agent uses its causal theory to predict incoming sensations, but also to predict what actions favor good experiences over bad ones. So the causal theory is involved in planning. So not all experiences are worthy of being acted on. So there we need to look at the concepts of attention and goals. The agent pays attention to the experiences that matter most to its survival, those it feels most intensely. So that will be primarily the ones that feel worse, but also the ones that feel best. The agent will assign itself the goals of impacting experiences that it pays attention to. Experiences it doesn't pay attention to will be neglected. The confidence an agent has in individual experiences will modulate how it responds to them. So an agent seeks to gain confidence in its experiences before it attempts to persist good ones or attempts to terminate bad ones. An agent has confidence in experiences that are not surprising, which is experiences that are not made up of many prediction errors, or if they are surprising, it will have confidence in experiences that are enduring. So even if it is surprising, the longer an experience persists, the more confident the agent will be about it. An agent will prioritize existential goals. It will prioritize its goals so that they maximize, so it maximizes its well-being. But when survival is not at stake, the agent can choose to act just for the sake of new experiences. It will pursue exploration goals. We say that it babbles. Okay, so having reviewed at a very, very, very top level the principles guiding this project, let's now look at its implementation. Implementing a robot that has agency does present significant challenges. Well, first, somehow the robot must be made mortal. So it has good versus bad experiences. Somehow, well, the robot must experience its world. It must make sense of its experiences and act to promote good one, and do that entirely on its own. Which means that the robot's experiences, its sense-making, and its goals must be entirely its own, not the programmer's. Now, what role does active inference play in the implementation of this project? Well, we have to recognize that active inference does not tell us how to program a mortal agent, especially one, as we'll see, that has an expanded cognition. That's fine, because that's not its purpose or intent. What active inference does is formalize what is required informationally for a self to persist in a dissipative world. So active inference provides us the requirements on the implementation of our autonomous agent. If I'm to be successful, the observable states of the robot will conform a posteriori to the requirements set forth by the free energy principle. Now let's talk about building a robot's mind. So how am I programming a mortal, experiential, and agentic robot? Well, my implementation draws inspiration mainly from cognitive biology, biosemiotics, and philosophy. I find inspiration in concepts from cognitive biology, such as the organism being mutually sustaining constraining processes, concept of multi-scale competency, stress as cognitive glue, problem solving in morphospace, and cognitive light cones. Those of you who follow the work of Michael Levin will recognize these as some of the key concepts underlying his work and the work of his lab. I also take inspiration quite a lot from biosemiotics, with concepts such as Umwelt, aboutness, signal processes, and sense making. And my two principal sources of inspiration are Dr. Terence Deacon and Dr. Jesper Hoffmeyer. I also lean pretty heavily on ideas that are coming out from philosophy. The application of Kant's metaphysics, its synthetic unity of our perception, plays a central role in my implementation, and we'll go into a little bit more details. And more specifically, I take very, very keen inspiration from the work of Richard Evans and his team in the development of the apperception engine. Again, we'll talk about this a little bit later. For you programmers watching this, the software is built using the Elixir and Prolog programming languages and an extension to Prolog called Constraint Handling Rules, CHR. So Elixir is a process-oriented and functional programming language. Prolog is a logic programming language, and CHR is a constraint-solving extension to Prolog. These are my programming tools. The hardware used in this project is a combination of the robot's devices plus a high-end server. On the robot, we find a set of Lego AV3 sensors and motors, a Raspberry Pi 3 for computing aspects, and a Dexter Industries BrickPi board that interfaces the EV3 sensors and motors with the Raspberry Pi, so they can be controlled through the Raspberry Pi. And the Raspberry Pi, of course, is connected through Wi-Fi to the network, making all of these devices remotely accessible. On the back end, I have a 128-core server that I actually do need to do the compute-intensive processing of various cognitive functions. Well, that's a necessary piece of hardware, because the computing power of the Raspberry Pi is far insufficient for what I'm trying to do. Okay, let's talk about mortal code. Can mortality be programmed? Can a robot be made mortal? Well, obviously the robot's physical structure is immortal. However, the processes that animate it can come in and out of existence. And if these processes implement, let's call it the mind of the robot, well, the robot's mind can be made mortal. So as it operates, as it explores its world, the robot will grow a mortal mind. This mortal mind is what animates its immortal body so that it can survivably explore and exploit the world it's in. And The goal is for the robot to learn to maintain sufficient well-being, or else its mind will die. I built a virtual grid world to provide a virtual robot with an environment that can both nourish, provide food, and damage the robot through obstacles and poison patches. The reason why I need a virtual world and virtual robots is just to accelerate development. If I were to do all the testing, debugging with physical hardware in a physical world, this would be largely unfeasible. But however, at some point, a physical environment will be built that recreates the conditions of this virtual world, but add all the unpredictability, messiness, and chaos of an analog world, which we can't do without to really fully test this implementation. All right, so we said that the robot will grow its mind as it exploit its world in order to capture what it learns. So let's talk about growing the robot's mind. More specifically, so what are the architecture and dynamics of this robot's mind? Well, first of all, I truly believe that all intelligence is collective intelligence, which means that the robot is not a monolithic agent. Its mind contains multitudes. So the robot's mind is implemented as a dynamic collective of cognition actors. So you should think of a cognition actor as a process that's part of a community of mind processes. It is the rich interaction between cognition actors that instantiates the agent's society of mind, its collective intelligence. Each cognition actor is implemented as a process that makes observations, which is a combination of predictions and prediction errors, unifies these observations into experiences, makes sense of these experiences, assigns value to them, are they good or bad experiences, and then acts to have better experiences. Each cognition actor in a collective of cognition actors has its own Umwelt. Umwelt, you can think of it as the self-centered world of a cognitive process, in this case, the cognition actors. So each cognition actor has its own Umwelt that it observes, makes sense of, and acts on. A cognition actor's Umwelt is made up of other cognition actors, except for the more low-level cognition actors who connect directly to sensors and effectors. So this collective of cognition actors that grows during the life of the robot is organized by their Umwelts and organized into abstraction layers. The bottom layer is populated a priori, so before the robot is turned on, by static cognition actors. These static cognition actors interface directly with the robot's sensors. I call them sensor cognition actors, and with motors. I call them effector cognition actors. Their own Umwelt is the robot's immediate external world. It's the distances perceived, it's the distance perceived, the ambient light perceived, it's the contact perceived. So, but the static cognition actors connect the robot's mind with its body's sensors and motors. So that's the bottom layer. All other layers come in and out of existence during the lifetime of the robot's mind. They capture, as I said, what the robot learns from striving to survive. So if the robot's mind is a collective, how does the collective learn to survive? Well, clearly the a priori bottom layer composed of the static cognition actors is not enough by itself for the robot to find nourishment and avoid hazards. Additional layers providing abstractions are needed to create the big picture experiences and affordances that are needed for competency and survival. Pure low-level perception and action are simply not enough. So, as we said, the first row is pre-populated by the static cognition actors, but all of the layers are populated by what I call dynamic cognition actors as the robot experiences its world and learns how to survive in it. We have to imagine that the society of mind grows, shrinks, reshapes itself by adding and removing dynamic CA as cognition actors. And for example, a dynamic cognition actors with insufficient well-being can trigger the birth, with sufficient well-being, can trigger the birth of another to fill a gap in Umwelt coverage. So obviously, we have a bunch of static cognition actors that are not in the Umwelt of a higher level one, so coverage is incomplete. And so we fill in this layer, and the layer must fill up before a higher level is started. There's a logic to the growth of this hierarchy of cognition actors. So as dynamic cognition actors are added into new layers, well, clearly they form an abstraction hierarchy. But it's not only growth. A dynamic cognition actor will remove itself if it persistently serves no purpose. If a dynamic cognition actor does not participate in another Umwelt, or if it's never called upon to share its experiences or to execute its affordances, if it's useless, it will eventually remove itself. And this will allow maybe new and different cognition actors to take its place and maybe be more successful. So this adding and removing of cognition actors and layers of cognition actors, in fact, explores the space of possible organizations of the mind. So let's say that this particular collective illustrated here is struggling to maintain the robot's overall well-being. Well-being is going down. This is not working. Death is impending. So we are searching for a competent collective, and this is not it. So the top cognition actor might remove itself, and it can because no other cognition actor depends on it. This allows for other underperforming cognition actors to also remove themselves, and so on, reducing the energy costs of the entire collective, and thus the loss of fullness by the collective. So we've essentially stopped the bleeding of fullness, of well-being, and we're now in a position to grow again. So the collective now having a lower energy draw can afford to regrow itself, and this time differently. There's a lot of randomness in how things grow. So the odds are that as it regrows itself, it will be different from the collective that existed before and was found to be insufficient. So the robot's mind searches for an organization of cognition actors that keeps it nourished and safe. The robot's mind is doing problem solving in morphospace. So what about experiencing? How's that implemented? Well, a cognition actor assembles unified experiences from its observations. Sensor cognition actors, so that these would be the static cognition actors in the bottom layer, have very simple experiences from observing distance, color, luminance, touch, etc. Their observations of sensor readings are their experiences. So while a static cognition actor observes and experiences the readings of its associated sensor, a dynamic cognition actor observes the experiences of its Umwelt cognition actor. So when a dynamic cognition actor is born, it is born with an Umwelt, a subset of the cognition actors from the layer below, and that's a static Umwelt. And this is what the cognition actor will be observing. It will be observing the experiences of its cognition, its Umwelt. But in order to observe it, it needs to predict. So the cognition actor in an Umwelt will communicate its experiential domain to the parent's cognition actors so that these can make meaningful predictions. An experiential domain describes the kinds of experiences a cognition actor has. So if I'm a cognition actor, I'm part of an Umwelt, my first task is to communicate to my parent. These are the kinds of experiences I have, so you can make predictions about the specific experiences I'm having. And that's what the parent cognition actor will do. It will observe its Umwelt, the cognition actors in its Umwelt, by predicting their experiences and then receiving or not prediction errors. And the observations of the parent cognition actor are the summation of predictions and prediction errors, but predictions of experiences of its Umwelt cognition actor. So there's a sense where the experiences of your children become your observation. But the parent cognition actor then unifies its observations into its own experiences. So multiple observations of its child cognition actor experiences will be combined into single experiences. So multiple observations of child experiences become a parent's experience. So for example, having observed in its Umwelt that distance keeps shrinking, a dynamic cognition actor would experience the more abstract concept of approaching. So the experience of a cognition actor becomes the raw material that are unified into the experiences of more abstract cognition actors, and so forth, all the way up from static cognition actors. So clearly, higher up dynamic cognition actors have more abstract experiences than the lower down cognition actors. For example, the experience of I stopped approaching is more abstract than the experience of approaching, which is more abstract than the experience of distance. It's worth noting that experiences are constructed and named by the dynamic cognition actors, and they're not constructed nor named by the programmer. In fact, they need not make sense to me as an external observer. So we talked about felt experiences. Where does the robot get its feelings from? The feelings it attaches to experiences so that the experiences are either good or bad or indifferent. Well, everything a cognition actor does increases or decreases its feeling of well-being. So well-being is determined, as we saw, by fullness, integrity, and engagement measures. Any internal or external work by a cognition actor reduces fullness in predefined ways. So for example, spending time over a food patch will be captured by a cognition actor as increasing fullness, or hitting an obstacle will be perceived by a cognition actor and it will reduce integrity. Cognition actor participating in an Umwelt will increase its engagement. So throughout its life, each cognition actor comprising the collective that makes up the mind of the robot will have fluctuations in its own well-being. And this fluctuating well-being determines whether a cognition actor's concurrent experiences feel good or bad. It might be good to note that well-being measures are not entirely separate. For example, activating motors is work that causes loss of fullness. It's an energy cost, but also a loss of integrity. We're going to be simulating wear and tear, while also increasing engagement. We are moving into our environment, so we are engaging. Lost integrity is regained over time. Think of healing, for example, but that drains fullness, and on and on. Now, if a cognition actor senses touch, when it senses a collision, it will have a loss of its integrity well-being measure. It will experience a loss. But it's important to note that the loss or gain in well-being of an individual cognition actor will diffuse throughout the collective. We can think of losing well-being as stress. So losing well-being causes stress. And stress is contagious. Stress experienced by a cognition actor in another's Umwelt will diffuse to the parent cognition actor, which will then diffuse downward to the children and upward, and eventually through the connections, the Umwelt connections of cognition actors. Stress experienced by one will diffuse and be experienced by everyone. And because a cognition actor cannot distinguish between a self-induced change to its well-being and a change caused by the diffusion of well-being from other cognition actors, well, one cognition actor's problem eventually, through diffusion, becomes every cognition actor's problem. Now, when a cognition actor feels a reduction in well-being, it feels stress, and stress alters its behavior. A stressed cognition actor is more likely to try something different from what has worked in the past. Obviously, something different needs to be tried. But a comfortable cognition actor, one that does not feel stressed, is more likely to settle into habits. Why change what has worked before? Now, let's take a little bit of a dive into acting. So, a dynamic cognition actor, again, it's part of a collective of dynamic cognition actors, acts for different reasons. One is to confirm its experiences, and then to terminate its worst one, or persist the better ones. So to confirm, persist, or terminate an experience, a dynamic cognition actor must first identify the observed Umwelt experiences that it unified into its own experience that it now seeks to impact. So the experience of a cognition actor is a unification of observed experiences by cognition actors in its Umwelt. So if I want to change, as a parent cognition actor, if I want to change an experience I have to understand its composition in terms of the observed experiences of my Umwelt cognition actors. Now, the cognition actor will plan how to alter these Umwelt experiences so as to impact its own experiences as intended. The dynamic cognition actor, each one has a causal theory, and we'll see more in details how it acquires it, that explains the observations it makes in its Umwelt. And thus it will use this causal theory to anticipate what would happen if experiences in its Umwelt were to change this way or that way. Would this achieve its goal of persisting or terminating one of its best or worst experience? So knowing how its own experiences are made up of Umwelt experiences, having a causal theory that explains how the observed Umwelt experiences change over time, then it can formulate a plan to change these Umwelt experiences in order to alter its own experiences. So question number one, as we said, which observed Umwelt experiences need to change to impact my experience, says a cognition actor. And then the cognition actor would say, okay, these are the changes that need to happen to the experiences in my Umwelt that I've observed and unified into my own experiences that I want to change. And it will then formulate a plan as a set of directives. And what's a directive? It's simply a desire to modify, impact an experience in its Umwelt. So it's basically a goal. A plan is a set of goals that are sent to the Umwelt for the Umwelt to accomplish. So the parent dynamic cognition actor sends goals to its Umwelt, goals to persist or terminate experiences that are being had in the Umwelt. But it doesn't tell its Umwelt exactly how to change these experiences. The Umwelt cognition actors will interpret these directives they receive and then make their own plans, because their experiences are also made of observations of their own Umwelts. So this way of, at a high level, saying, I want you to accomplish this, and then at the lower level say, okay, fine, and I'm going to decide on my own how to accomplish it, and then ask the lower level to do the same. This implements a multi-scale competency. Again, for each goal it takes on, a cognition actor interprets it as directives, planned directives that it then sends to its own Umwelt for them to interpret, and so on. So action goes all the way down, from the top to the bottom, all the way down to effector cognition actors, where a directive might be simply to spin a wheel. Now, a dynamic cognition actor keeps track of directives as sent and the goal they are meant to achieve. Directives that appear to have achieved their goal are remembered as affordances for later reuse. Effector cognition actors, at the very bottom, have atomic preset affordances such as spin or reverse spin. Whereas the cognition actors higher up, the dynamic cognition actors, discover abstract affordances such as go forward or even go up the luminosity gradient. So as you go up the abstraction layer, the affordances become more abstract, more high level. Affordances are discovered and named by the dynamic cognition actors, not by the programmer. That's important. And in fact, then they don't even need to make sense to an external observer such as myself, the programmer. Now, let's look at how cognition actors build the causal theories they use to predict incoming observations and plan their actions. So, a cognition actor observes its Umwelt one time frame after another. And a time frame is a thick now. And the more abstract the cognition actor, the longer its time frame. So we could say that a more abstract cognition actor has a bigger cognitive light cone, if you wish. And observations made within a time frame are considered synchronous. So even though they may be made sequentially, so within a time frame of, say, let's say half a second, 2 seconds, 5 seconds, they are considered to be concurrent, to be happening at once in the real world. So a dynamic function actor constructs its causal theory to make sense of what it observes within each individual time frame. And this causal theory, this construction of a causal theory, is a form of induction, that is the production of general rules from specific examples. Examples being the observations. A causal theory here is a set of if-then rules in the program. It's a set of if-then rules that are constructed and live about three kinds of things. What observations ought to occur at the same time, in the same time frame? What observations cannot coexist in the same time frame? They're mutually exclusive. And what observations would follow from previous observations? For example, we might have this causal theory that says if the distance is getting shorter, then nothing is being touched. So if you are observing that the distance is getting shorter, you should also be observing that nothing is being touched. And if you don't, you can infer that nothing is being touched. Another constraint, another rule, which is a constraint here, that says the distance cannot be getting both smaller and larger at once. So you cannot have these two observations coexisting. And a third rule, which is more of a causality rule proper, is if both wheels spin forward, then the distance will get smaller. So this rule predicts what happens in the next time frame. So this is an example of a causal theory. An interesting side note is that causal theory can posit hidden, that is latent facts, that are needed to make sense of actual observations. So a causal theory can be partly an act of imagination. And this positing of hidden facts is a form of abduction, that is the inference of likely causes from effects given general rules, for those who enjoy logic. So the discovered rules that make up the causal theory are expressed in the implementation as a logic program. The logic program embodies a causal theory, and it is constructed without human intervention. Learning is achieved entirely from experiencing. There's no prior instructions or feeding of examples before the robot is turned on. And this type of learning happens repeatedly over the lifetime of a cognition actor, and it happens for all cognition actors making up the collective, the mind. So the logic program serves as a generative model. You can feed it the current observations, and it will produce the predictions of the next observations. Each dynamic cognition actor constructs and runs its own logic program, though at first they run the same trivial program. So the whole thing bootstrap with every cognition actor have a simple program that says it is as it is and nothing ever changes. And so the dynamic cognition actor will run its logic program to predict the next observations, but also to do what-if reasoning before acting. Okay, so when predictions made from a causal theory result in too many prediction errors, that's because the causal theory is inadequate, then the dynamic cognition actor will replace it with a better one if one can be found. So how are these logic programs that embody causal theories generated? Well, by an apperception engine. The apperception engine is a computer process that inputs a cognition actor's observations and outputs a causal theory that explains them. So you feed in a history of observations, turn the crank, out comes a little program, logic program, that if you feed it the latest observations will produce the likely next set of observation in the next time frame, the predicted observation. So when they need a causal theory, and they will need pretty quickly, especially in the beginning, dynamic cognition actors call upon the apperception engine as a service when they need to replace their current causal theories. Again, they do so because they experience too many surprises when using their current causal theories, or they fail consistently to predict the consequences of acting upon their umwelt. Now, finding a logic program from remembered observations, one that makes accurate predictions about future observations, is a difficult search problem. It's a hard nut to crack. Because the space of all candidate logic programs, where the haystack, if you wish, is ridiculously large. So to find a good enough program in what I call useful time, while it's still useful to have that logic program, the search needs to not look over the entire haystack. It needs to be biased so it productively ignores much of the search space. That's where the work of Immanuel Kant comes in. Is synthetic unity of apperception, it's part of its metaphysics, focuses the search on causal theories that are coherent and possess explanatory power. So Kant's theory says these are the properties of causal theories that are worthy. They are coherent, they have explanatory power, and you can ignore any causal theory that does not have these properties. So the apperception engine is a program that applies Kant's synthetic unity of apperception to find logic programs that encode coherent and useful causal theory. So the original apperception engine was built by Richard Evans et al. At Google DeepMind, and I simply, quote unquote, re-implemented and optimized it. And it was a subject of my presentation last year. And there's a paper on that you can read to find more of the details. Okay, so all in all, this project aims to express and connect all of these concepts into working code. And this code will animate a mortal and adaptive robot that is capable of agency. That is the task. So where's that code? Well, it's the open source project that I'm working on that contains this code and design notes is called the Karma system. In all the code, all the notes are completely open sourced, and here you have the URL of the GitHub repo, which you can go see and peruse. There are a number of sub-repos under the Karma system. There's one with a Prolog actor framework. The actor framework is kind of the runtime platform for the cognition actors. There's a implementation of a practical apperception engine. There's code that implements agency, so code that implements the actual cognition actors, a bunch of utilities. There's code to implement the logic on the body of the robot itself, so the access to the sensors and motors. There's an implementation of a virtual simulation environment, Karma World, and there are other repos to come that will provide an experimental platform so I can run experiments, collect information, collect data, and submit this data to analysis. So these are the main subsystems of the Karma system, and they communicate over a network. So that's how the sensors and motors can be accessed on the robot and by the cognition actors running on the backend servers, so that it forms a unified system. Bit of a progress report here. Well, a lot of things have been accomplished, done. I have a detailed conceptual and implementation design that's documented in the Karma system repo. The interface of the robot's sensor and effectors is implemented and working. I have a virtual grid world that's also functional. The apperception engine is running and seems to be doing well. I have a runtime platform for cognition actors. And I have implemented the static cognition actors for that interface with sensors and effectors. So that's code that works, tested. What's in progress right now is the implementation of the dynamic cognition actors, and that's in the Karma agency repo. What's haven't started yet and still to do is a physical recreation of the grid world, implementing the observer and analyst subsystems. So observer to collect the data from running the robot, analyst to subject them to analysis, more specifically to validate that the requirements from the free energy principle are realized in the data that we captured from running the robots. Then and of course, doing the experimental runs and collecting the data and doing the free energy principle data analysis. That's to do. Now, a parting thought. Now, should I succeed at programming a robot that has felt experiences, makes sense of its world, and strives to survive, could there be something it is like to be this robot? I, for one, don't know. But if you answer, definitely not, then I do have follow-up questions. All right. So here's how I can be reached. Email, and I'm on the SimCog Robotics channel in the Active Inference Institute's Discord. And you have here the URL to the top of the GitHub repo. So I'd like to conclude by thanking the Active Inference Institute for giving this project a supportive home. Thank you.